Good morning. Welcome to today's presentation on how to select and size a pressure-reducing regulator, brought to you by Swagelok Northern California. I'm your host, Rebecca Donaldson, and I'm joined today by a leading regulator expert, Eric Kala, a field engineer with Swagelok. Eric will discuss selecting a regulator, understanding regulator flow curves, and how to use flow curves to properly size your regulator. We will post a recording from today at norcal.swagelok.com. During the presentation, please send any questions you have via the chat box, and Eric will answer them after the main presentation. And in the next few days, we'll send you a pre-release copy of the new guide, Pressure Reducing Regulators, a guide to finding the right fit. Eric Kala joined Swagelok 17 years ago. He started at Swagelok as a lab engineer working on high-purity fittings and pipe fittings. He's since worked in new product development and assembly engineering. Today, Eric's based in San Diego as a field engineer. He spends at least half of his work life on the road, meeting with customers in the western U.S., Canada, and Mexico. Let's get started with how to select and size a pressure-reducing regulator. Eric?
Good morning. Thank you, Rebecca. As Rebecca said, this morning we're going to talk about regulator selection and sizing. The first thing we're going to do is review our operating principle of our pressure-reducing regulator, which is our balance of forces. We'll talk about a few items that you can consider when you're selecting a regulator, including whether to go with a diaphragm or piston sensing regulator. We'll talk about regulator sensitivity and resolution, and then we'll move into sizing a regulator. We'll talk about why not to use C sub V for sizing, talk about the requirements that you have to know when sizing your regulator, including inlet pressure, your pressure control range, and your flow requirements. We'll then talk about how to read a flow curve, and finally talk about some correction factors. Lastly, we'll cover a few other considerations to make and hit an example of sizing before we end the presentation. A pressure-reducing regulator is designed to take a high inlet pressure and reduce it to our set outlet pressure and keep that set outlet pressure as constant as possible, regardless of changes to the inlet pressure or changes to flow downstream. We can look at our pressure-reducing regulator and look at really three areas of operation inside the regulator. The top part of the regulator is our loading forces. And in the case of the regulator cutaway here, we see that we have a spring-loaded regulator. On the bottom part of the regulator, we have all of our internal forces. And those are highlighted by our high inlet pressure as well as our low outlet pressure. Both of these areas are balanced across the sensing mechanism. And the sensing mechanism in this case is right in the middle of the regulator. And the example shown here is a diaphragm sensing regulator. If we think about a regulator as a seesaw, on one side we will have our loading force, typically a spring force. On the other side we'll have our internal forces, the inlet and outlet pressures. Both of these being balanced across that sensing element in the middle of the regulator. Looking at it a little more technically, we can put together a balance of forces equation. So we have our F1, our loading force coming in from the top, a small contribution from an inlet spring force on the bottom, our outlet pressure force, and then our inlet pressure force. And if we push this into an equation, we'll have our loading force equal to our internal forces within the regulator. Now, as we move into selecting a regulator, the first thing that we're going to really consider is whether we want to go with a diaphragm sensing regulator or a piston sensing regulator. And there are some key differences between the two designs. A diaphragm sensing regulator has greater sensitivity and typically a wide range of material choices that might be available for that diaphragm. The diaphragm could be metallic, it could be an elastomer, or it might be some sort of plastic like PTFE. For a piston sensing, they are higher pressure regulators, but they tend to be less sensitive than the diaphragm sensing regulators. When we talk about sensitivity, it's good to take a step back and define what sensitivity is. And sensitivity is the minimum set pressure increment that can be repeatedly set in flow conditions. And what this translates to is it basically says sensitivity is how well your sensing mechanism reacts to changes in pressure inside the regulator. A regulator's sensitivity will increase with a larger sensing diameter. So as our diaphragm or our piston get larger, our sensitivity is going to increase. And then the diaphragm design, as we discussed previously, is more sensitive than the piston design. Resolution in a regulator is the change in outlet pressure as you turn the handle, or as you adjust the handle in the regulator. And this is typically measured in a no-flow situation. It can also be described as the number of turns to dial through the outlet pressure range of the regulator. So as we look at this in a couple of examples, the regulator graphic shown on the left, in this regulator we can get to 125 psi outlet pressure with 3 turns of the regulator. The graphic on the right, with this regulator we can get to 30 psi with 3 turns of the regulator. And the question comes up is, which of these regulators would be easier to set to 15 psi? We could set both of them to 15, but which one's going to be easier to do? If we look at the one on the left, it looks like we can get to 15 psi just short of half a turn. But because we've got 50 psi through that full first turn, we're going to have a pretty gross adjustment to reach 15. The graphic on the right, we can reach 15 psi outlet pressure with approximately 1.5 turns of the handle. Because we go through 10 psi at one turn and then hit 15 about halfway through that second turn, we're going to have a finer adjustment with that second regulator. So resolution really is going to define is how fine of an adjustment you can make on the regulator. Now moving on from those considerations when you're looking at selecting a regulator and really getting into the heart of the discussion here today, we're going to talk about sizing the regulator. And the first thing we're going to do is talk about C sub V versus the flow curve. We'll talk about what we need to know in our inlet pressure, our outlet pressure, and our flow requirement. We'll discuss the characteristics of the flow curve, and finally we'll talk about how to use the flow curve. Quite often, people will try to size a regulator using the C sub V, and that's really not an appropriate way to do it. The C sub V is the flow coefficient of the regulator. It's a flow coefficient of anything that it's assigned to. A lot of valves are sized using C sub V. It's just not a great way to size regulators. In technical terms, C sub V expresses the flow capacity in gallons per minute, and it's the amount of, or the gallons per minute of water that will pass through the regulator over 1 minute with a 1 psi pressure drop. In our regulators, this is a relative measure of flow across the seat of the regulator, and it's calculated when the regulator is in a fully open position. Now, we never want to operate our regulators in that fully open position, so C sub V really only tells us the maximum amount of volume that can go through the regulator, not the volume that will go through the regulator in the pressure range that we want the regulator to operate at. So C sub V might be useful in comparing different regulators between each other. It's really not a great way to size a regulator. The best way to size the regulator is to look at the flow curve. This is an example of a flow curve shown on the screen. Flow curves are very typically developed from testing. So what you're looking at is going to be data that has been derived from physical testing of regulators. They're typically tested using nitrogen or air, and typically at 70 degrees Fahrenheit. Now, when we talk about using a flow curve, there's things that we need to know. The first thing we need to know is our inlet pressure. This is going to be the high pressure coming into the regulator, the pressure that we're starting with before we reduce it down. The next thing we need to know is our outlet pressure. This is going to be the target pressure out of the regulator when it's in operation. And the last thing we need to know is our target flow rate. And our target flow rate is probably going to be a range. It's very unusual to have a single flow through a regulator constantly. They typically have a range that they're going to operate within. So with these three pieces of information, we can find and select a curve that will meet our application, and from there will lead us to the proper regulator for our system. Now let's look at a couple different aspects of the regulator flow curve. The first thing we want to be aware of is what is called droop. And droop is the reduction in outlet pressure as flow rate increases. So as our flow increases from left to right across the bottom of the flow curve, we'll notice that our pressure curves tend to drop off. And this phenomena is called droop. Another thing to be aware of in our flow curves is lockup. And lockup is what occurs as we go from a flowing situation to a zero flow situation. So we're traveling on our flow curve from right to left, and as we approach the zero flow line, or the vertical axis, we have a sudden spike in pressure. And that spike in pressure is called lockup. If we look at the far right-hand side of the flow curve, where the flow curve kind of ends, this is what we call the choke flow point. And the choke flow point is when the regulator is in the fully open position. So it's no longer acting as a regulator, it's really just an orifice in the system. Now interestingly, the choke flow point is where the C sub V is calculated. So you can see that C sub V is not a great way to size your regulator, because you're sizing it way out on the end of the flow curve where it's no longer doing the job that you want it to do. And then the last thing is really where we want to be using the regulator, and that's our optimal flow range. This is the range on the flow curve where we're going to get the best performance of the regulator. We're far enough to the right that we're out of the lockup area, but we stay away from the choke flow point. And we're typically looking at maybe 2/3 to 3/4 of the full flow curve on the regulator as our optimal flow range. We will still have droop in the optimal flow range, and that's something that we're just going to have to work with and size our regulator appropriately to account for. So if we bring it all together, we still see we have droop on our flow curves. We can see our lockup area. We can identify our choke flow points, and we can identify our optimal flow range. And knowing these things will help us as we move forward to sizing a regulator. Now, if we want to size a regulator, if we know what our inlet pressure is going to be, we know what our outlet pressure is we want for our system, and our flow rate for our system, we can plot a point on our flow curve. So in the case shown here, we've got just over 1,000 psi inlet pressure, 175 psi outlet pressure, and a desired 425 standard cubic feet per minute flow rate. This identifies that we should be using that middle A flow curve, that middle A regulator, for this application. Now this is all very easy if we find a point that is exactly on our flow curve. But what happens if maybe the regulator, or that our application is not on the flow curve for the regulator that we think would work for the system? And when that happens, we can actually move and interpolate along the flow curve. So if I have a flow curve, as shown on the screen, and this is starting at 200 psi outlet pressure, but I really need to operate at a different pressure, I can slide those curves up and down on that y-axis. So now instead of 200 psi, I've dropped my curves down to 175 psi. So the shape of the curve is staying the same, we're just sliding it up and down on the axis. Now if I drop the curve all the way down to 100 psi, that's close to where I'm going to be operating, and I want 30 standard cubic feet per minute, my outlet pressure is going to be 80 psi. And maybe that's great and that's going to work with my system. Something else that we might run across as we're looking to size our regulators is that we'll have an inlet pressure that is different than the inlet pressure shown on the flow curves. So the flow curve shown here, we have inlet pressures of 2200 psi, 1000 psi, and 500 psi. But what if my system has maybe 1500 psi as the inlet pressure? Well, at that point, we can interpolate between the 2200 psi line and the 1000 psi line and kind of estimate where that 1500 psi line is going to be, and then use that interpolated line for our sizing and for the application. One thing to keep in mind for interpolating on the flow curve, as well as moving those flow curves up and down, when you start doing this, it's not going to be as accurate as the published flow curves. Again, the published flow curves are based on testing. When you start interpolating or moving the flow curves, now you've gone from having data based on testing to based on an estimate. So there might be a little bit of trial and error when you get the regulator and install it in the system, but you're going to be very close, and it's going to really help you get the right product into the system. When we first started talking about our flow curves, we said that the flow curves are usually tested using air or nitrogen. Well, the question would come, what if I'm using something, another gas other than air or nitrogen in my system? And what we need to do is apply a correction factor for the other media that's being used if it's different than the media that the flow curve was tested with. And what we're trying to do is create a correction factor based on specific gravities. So if we look at the specific equations we're looking at, we'll take the specific gravity of our reference fluid, typically nitrogen or air, divided by the specific gravity of our actual fluid, and take the square root of that to get our correction factor. Nitrogen has a specific gravity of 0.97, so we can adjust our equation to be 0.97 divided by our actual specific gravity for those flow curves that are using nitrogen as the gas that the flow curves are tested with. Most manufacturers are going to publish a table of correction factors with their flow curves. So instead of having to do the division and taking the square root, you can just pull the correction factor for the appropriate gas off of the table and apply that correction factor to your application. And how this looks, it can be explained in a quick example. The correction factor for carbon dioxide is 0.80, and we pulled that from the table on the last slide. If we have a flow curve that tells us the nitrogen flow rate is 100 standard cubic feet per minute, the equivalent flow for carbon dioxide is going to be that same 100 standard cubic feet per minute times our correction factor, 0.80. That's going to give us a flow of 80 standard cubic feet per minute. And what we need to keep in mind is that the curve is going to remain the same. The scale is what's going to change. And this is the same idea when we talked about moving the curves up and down. The shape of the curve is always going to stay the same. Those curves, again, are based on testing, and the shape of the curve is really telling you a lot about the physical aspects of the regulator. Your seat diameter, your poppet dimensions, and so forth. So the shape is not going to change, but now you're just moving that, adjusting the scale across the bottom, or sliding that curve up and down on your axis. We also talked about the testing for the flow curves being done at a specific temperature, and that temperature is typically 70 degrees out. So if we are using the regulator at a temperature other than the tested temperature, we need to apply another correction factor for temperature. And these correction factors are applied in exactly the same way that the correction factors for gases are applied. Note that if you're using a different gas than the regulator was tested with, and you're using it at a different temperature, you're going to have to apply both correction factors. And as we mentioned before, the shape of the curve doesn't change, just the scale, the flow scale across the bottom of the flow curve is what we're adjusting. So moving on, we're going to talk about a couple of other considerations that you're going to have to make when you're selecting your regulator, and then get into an example. So the first thing to consider once you've identified the appropriate regulator model is now selecting the port configuration. And there's many port configurations available from all the different manufacturers. Right to left flow, left to right flow, inlet gauges, outlet gauges, relief valve ports. All of that is really up to you and your application. But it is useful to understand how that porting is machined into the regulator itself. It's easy to understand when you have straight through flow from inlet to outlet, but as you start applying gauge ports, relief valves, things like that, then now you've got different ports, different machinings that are happening in the system. So for instance, if you apply gauge ports to your regulator, but you're concerned about maybe hold-up volume for an analyzer, you're going to get significant hold-up volume in the regulator and into that gauge leg. So is it worth it to have the gauge in the regulator itself, or maybe is it worth it to have that gauge on a separate shorter T just downstream from the regulator? So things to consider as you're selecting what porting configuration to use. Another consideration is going to be whether you want a venting regulator or not. A self-venting regulator will allow you to adjust the outlet pressure and either increase or decrease that outlet pressure in a zero flow situation. So you have no demand downstream, but you're still able to increase and decrease the pressure at the regulator. If we compare that against a non-venting or a non-self-vent regulator, we'll still be able to increase the outlet pressure in a non-flow situation, but we will not be able to decrease the outlet pressure unless there is demand downstream. So for the non-self-venting regulator, we can continue to increase our pressure and we'll see the pressure at the regulator rise, but unless there's demand and flow downstream to use up that additional pressure, we will not be able to drop the pressure of the regulator. So we're really dependent on what's happening downstream. And there's applications where you want to use self-venting, and there's other applications where you don't want to use self-venting. And that's important to think about as you're finally selecting the appropriate product for the application. There are typically 4 venting options when you're looking at the possible regulator for the application. The first is a very standard non-self-venting regulator with no captured vent. So this is the regulator that if there is no demand downstream, we won't be able to back the pressure off at the regulator. It has that static pressure between the regulator and the equipment or device, and if it's not flowing, you will not be able to drop the pressure. Next, we have a self-venting regulator with no captured vent. This is the self-venting regulator that you can increase or decrease the pressure at the regulator in a non-flowing condition. Next, we have a non-self-venting regulator with a captured vent. And the captured vent is actually a threaded port, typically an NPT thread, off the top part of the regulator that allows you to capture the gas or the fluid that is being vented from the regulator and either recycle it and reuse it or vent it away safely to another location. In this case, this is a non-self-venting regulator, so there won't be any venting happening through the regulator. So you might wonder, why would I have a captured vent port? Well, in this case, we would use that captured vent port to monitor the health of our sensing mechanism. So if we're running a potentially hazardous media through our regulator, and we want to make sure that we've got a healthy sensing mechanism, a healthy diaphragm, for instance, we might put some sort of sensor or an alarm into our captured vent port to alert us if we start to get a leak across our sensing mechanism and let us know that it's time to do some maintenance on that regulator. The last option is going to be the self-vent with captured vent. And this regulator is again the self-venting option, so we'll be able to increase and decrease the pressure at the regulator even if there's no flow downstream, but we still with this one can then capture that fluid, the gas, off the regulator when you vent it, and then either vent it safely or capture it to reuse it. So the last thing we want to talk about this morning is an example of sizing and selecting a regulator. So let's look at our parameters. We have argon gas supply to 2 pieces of welding equipment, 2 welders. The equipment is in an enclosed clean workspace and has an inlet pressure of 1500 psi from a stable argon header. Our required control pressure, or our outlet pressure, is 50 psi. They're giving us a little bit of a range. We can go plus or minus 10 psi on that outlet pressure. And our flow requirement is going to vary between 15 standard cubic feet per minute to 30 standard cubic feet per minute. This is probably because we've got 2 pieces of equipment. We might be operating 1 piece or both pieces of equipment at any given time. So something to be aware of there. It's important to know on the inlet pressure that we've got a stable inlet pressure. And stable can mean it's not going to fluctuate too much, which is important, but it's also important to know whether that inlet pressure is coming off of some sort of compressor or pump. If you've got a compressor where you might have some small pressure fluctuations or pressure vibrations in your fluid, that's going to point you more towards a piston sensing regulator and less towards a diaphragm sensing regulator. In this case, it says it's stable, so we'll consider going with a diaphragm sensing regulator. So we've looked through a bunch of flow curves and identified an appropriate flow curve for our application. And as we look here, the 0 to 50 psi control range, the blue lines, aren't appropriate for our application. With the Droop and the Lockup, they end up well below our target pressure of 50 psi plus or minus 10 psi. So we actually have to go with the 0 to 100 psi control range, and we're fortunate that our 1500 psi inlet pressure, even though it falls between the 2 inlet pressures on the graph, both the 1000 psi line and the 3600 psi line are the same line. So we don't have to do any interpolation. But what we do have to do is slide our flow curve down a little bit into the range that we're going to be using the regulator at. So we slide our flow curve down, and then we plot our application. So 50 plus or minus 10, our pressure range is from 40 to 60 psi, and our flow rate is from 15 to 30 standard cubic feet per minute. So once we drop the flow curve, we see that we're at 60 psi at 15 standard cubic feet per minute. We're at 40 psi at 30 standard cubic feet per minute. So regardless of what flow or where we're at in our flow range for the application, we'll always fall within our pressure tolerance. So this is a good regulator to select for the application. The only other thing to consider is what else do we need to be aware of? And an important consideration might be that the equipment is used in an enclosed, clean workspace. So you may have to ask some follow-up questions. How well ventilated is that enclosed, clean workspace? If we use a vented regulator and we're going to be venting argon into an enclosed workspace that doesn't have good ventilation, that becomes a health issue and a health hazard for the welders that are working there. So in this case, if we decide to pick a vented regulator, we might pick the self-vent regulator with the captured vent. So as the argon is vented out of the regulator, we can capture it and then pipe it away safely and dispose of it at a point where it's not going to be dangerous and cause an asphyxiation issue in that enclosed workspace. Okay. And that's the end of the discussion we wanted to have today. Are there any questions that we can hit here today?
Thank you, Eric. Some questions have come in. One is, can you interpolate below the lowest published flow curve?
That's a good question. Let me back up a second. And if we just look at this graph, in this case we moved the line vertically down. So we went from that original LR and W black line and slid that line down into that second blue line. And that's sliding up and down the Y scale, which we talked about earlier. But if we wanted to use a regulator at the 0 to 100 psi control range, which are the black lines on this graph, but we wanted to use it at maybe a 75 psi inlet pressure. So we see our F line is our 100 psi inlet pressure, but if we want to go below that, it's much more difficult to interpolate below the flow curve because you only have a frame of reference on one side. So when we talked about interpolation being a good estimate, when you get below the lowest flow curve, because you don't have a bottom line, a floor really for your estimate, it's becoming a much rougher estimate. It's something that you can do, but it's not going to be as accurate.
Why would someone use a left to right over a right to left flow?
That's really going to be dependent on the application itself. So where's the regulator going to be installed? Where is the high pressure located? Where does the lower control pressure need to end up? And once you see where the application is, you can decide left to right flow or right to left flow.
What happens if you operate the regulator outside the optimal flow range?
If we go outside the optimal flow range, and we'll back up to one of our previous slides real quick, depending on which side you operate on, if you're outside the optimal flow range, you're either going to be operating towards your lockup area. So this is really below the usable flow range of the regulator. You're going to have very erratic pressure and flow readings when you're operating towards the lockup area. Alternately, if you're operating the regulator beyond the optimal flow range, you're going to be way out and close to your choke flow point. So the regulator is not going to be doing a whole lot of work. It's going to be more open than closed, and it's going to be acting as more of a restrictor in the system and less as a pressure regulator. Good question.
Can you minimize droop, and if so, how?
Droop in a regulator is a function really of the mechanical construction of the regulator. So it's something that we have to deal with in the regulator. It's not something that's easy to eliminate. But to minimize droop, you can go from a spring-loaded regulator to a dome-loaded regulator. And that helps really to start to flatten that flow curve out. There's some different options that we can apply to those dome-loaded regulators to continue to push that flow curve closer to horizontal. And ultimately, the best thing we can do is put an electronic pilot regulator onto a dome-loaded regulator. And that really comes very close to giving us a horizontal flow curve with just a small amount of droop.
Last question. What if we think some of our regulators were sized using the C sub V method?
If you do think that you have regulators in your system that are sized using the C sub V, then your regulators are sized at their choke flow point. So in the graph we're looking at here, your regulators are sized all the way out on the right-hand side of the flow curve. So you're really not able to take advantage of the optimal flow range. It's going to affect the resolution of the regulator that we looked at earlier. You're not going to have a whole lot of adjustment that you're going to be able to make on the regulator. You're probably going to find that your handles turn fairly far in on the regulator. And it's really probably not going to be giving you the type of performance you'd like to see. So it's much better to be able to size those regulators for that optimal flow range.
Thank you, Eric. If you'd like to consult with Eric, please call our office at 510-933-6200 to set up an appointment, or use the request information page at our website. We'll post a recording from today at norcal.swagelok.com as soon as we can, and in the meantime, we'll send you a copy of the new guide to finding a right fit that's coming out shortly. Thank you, Eric, for sharing your expertise, and thanks to each of you for participating.